in the lecture. So let's continue with the result about the non-existence of complete curve in the stratum of meromorphic differentials. Let me recall the result. So the theorem is the following. Meromorphic just means the differentials have some poles, so some signature mi is negative, so some mi is negative. Then the result says this H m1 mn does not contain any complete curve. Okay, so I'm going to present you the proof. The proof is not very long, but it depends on some calculation on moduli spaces, and I need to introduce some Lamb-bounded classes, divisor classes. So some of you know this, but I'll just recall the basic definitions of these Lamb-bounded classes. Excuse me, let's do, before I do the proof, maybe let's try to set up some notation and definition. So let's consider the following. So in general, let B. So B, so parameterize a family. Let me put it this way. Let's call it pi from so curly x to B. Be a family of genus G curves with n markings or n marked points. So the picture you should have in mind is that suppose B is something like like a base, and then X is a fibration over B. Each fiber is a genus G curve. Okay. So maybe I can consider stable genus G curve, but in this case I can consider even smooth genus G curves, assuming there's a complete curve. This modular space parameterizes smooth curves only, so it doesn't matter. Let's draw smooth fibers only. So each fiber is a genus G curve. As a fiber, so X is here, so this is pi. And in addition, so each fiber is not only a genus G curve. I said it has n markings, right? So in the family, that means I can connect these n markings as sections from B to X. In other words, I have sections from B to X. So maybe let's call these sections S1 up to Sn, okay? So maybe let's draw another one. So there's a morphism, actually an isomorphism from B to each section. So it's the I section Si. Now you think of this section and the intersection on each fiber, and each fiber gives you an n-pointed curve, right? This is a genus G curve. I have n sections. There are n intersection points. So this means I have this fibration, and so let's call it this map from B to each section Si, so I call sigma I, and sigma I from B maps to X for I. So I need n marked points. That means n sections for I from 1 to n. These are like marked points, or sections of marked points. Okay. So that's how you think of a family of genus G curves with n markings. So all right, once you are in this situation, So let me introduce a few Lambda classes or divisor classes. So each fiber is a density curve. I can consider the so-called relative canonical line bundle or relative cotangent line bundle. That means I want to consider the canonical line bundle not of the total thing, but restrict to each fiber. It canonically represents the canonical line bundle of the fiber and varies canonically with the base. So let omega, this fibration is called pi. Let's just call it omega pi be the line bundle class be the relative, canonical line bundle class of the fibration pi. Okay. So more precisely, as I said, that means omega pi. So omega pi is still a line bundle class on the total surface, on the total family X, but omega pi restrict to each fiber. Let's call each fiber say X. It's canonically isomorphic to the canonical bundle of X. Okay. And there's a more intrinsic definition using. You can think of, I have the canonical line bundle of total thing and the modulo the pullback of the canonical bundle from the base. Okay. All right, so that's the first thing I want to introduce, the relative canonical line bundle. Okay. So another thing that I want to introduce another thing. So let's consider, like, again for each I from 1 to n, let's the so-called psi class. So this psi class actually lives on the base B. Maybe I should say the lemma class. So this guy is still on the total surface X of F pi. So omega pi is still a line bundle on the curly X. I now want to define the line bundle class psi I on the base B. Defined by look, so I just defined omega pi as a line bundle on the total family. I can restrict omega pi to each section Si and pull back this line bundle restriction Si back to B. You can think of B and Si, they are isomorphic. And because Si is a section, you map B to Si and map back to B by pi. In other words, sigma I composed with pi is identity. But the map from B to each Si may look different. So I restrict the line bundle omega pi or any line bundle to S1, it may look different from the restriction to S2 because these are different sections. So I get n of them, so I just define each Fi, phi I, be as definition given by sigma I as this section, B maps to Si. I can pull back the line bundle omega pi. Okay, so omega pi as a line bundle on the total family, I restrict to the I section, I then pull it back from sigma I. So this I usually called the cotangent line class associated to the ith marking. Maybe I should also write it down, sorry. I'll explain this in a second, cotangent line bundle class. Sorry, so here's with respect to the ith marking. So in other words, if you think of, so this psi I, because I pulled back to B, so this is defined on B, right? If I take a point which represents this fiber X, right? You think of B as a modular space, say MGN or MGN bar, that's what you really should think. So this is a universal curve. Then if I take this point in the modular space representing the fiber with the n markings, so what is a line bundle psi I is fiber over that point? So let's call this point representing the class X along with these markings. Let's call them maybe P1 up to Pn with this marks point Pi. And then psi psi I as a lambda restrict to that point, I can canonically describe its fiber. This is isomorphic to, canonically isomorphic to, as a cotangent line that is really the canonical bound of X. Its fiber restrict to the ice marking, so restrict to the point Pi. So this follows from this definition directly, right? Because omega pi restrict to each fiber is a canonical line bound. Now I further restrict to the I section. The I section just the mark point Pi. So that tells me my phi I is really the fiber over this point, stands for the canonical space, sorry, the cotangent line space associated to the ith marking. Okay. So these are some formal definitions, but there's one important thing. So let's leave the definition here. So when I use it, I'll let you know. So let me move on to define one final class. But then I need a little more data, because this result is not only about a family of pointed curves, right?
What's confusing this? But this n and that n is different, right?
Which n and that n?
It's P1 to Pn. These are only the negative.
No, these are like all zeros and all. I have these n special points. I just mark all of them.
Right.
Yeah, so I'm saying, so I should say, okay, so far this part has nothing to do with the theorem. I'm saying I introduce these divided classes. But then I can apply it to this case, right? Because if I have a family, say a complete curve, this actually I will use this B to stand for, suppose I have a complete curve, which I call it B. Then over B, I will have a family of curves with n special points, right? Because these are distinct points. Those are, I will call them S1 up to Sn. And these P1 up to Pn are exactly either zeros or poles.
Distinct points are exactly the number of negative sign.
No. I'm not saying. There could be positive or negative. I include all of them. Okay, maybe now let's come back to the content of the theorem. So I'd like to keep this picture, so let me erase this definition. Hopefully you have written on your notes. So I erase this part. Okay, so let me come back to the proof. So let me prove it by showing contradiction. Okay, so proof by showing contradiction. In other words, suppose there exists a complete curve in this stratum Meromorphic difference. I will give you a contradiction. Okay. So let me actually still denote this complete curve by B. Okay. Sorry. This H. So this is a complete curve. Okay. So then what does this mean? So let's mark the n zeros, all poles. I include all of them. Okay, I have these n special points. They never intersect each other because I require they are distinct zeros and poles. That's the meaning of being a strata, right? If they merge, it goes to a different strata. So these are all distinct points. And then that tells us B can be viewed as a family of n-pointed curves, right? Because each curve here, parameterized in B, carries n distinct zeros and poles. Okay, these are I still call them P1 up to Pn, and they vary in the family. I still use this picture as well up to Sn, and B becomes a one-dimensional family of pointed curves. Okay, so then B is a one-dimensional. B is a complete curve, complex one-dimensional family of n-pointed curves. So I can use this picture. So all the divisor classes I defined earlier make sense to apply. Okay.
So there is a natural map from this H M1 to Mn.
Oh yeah, just by marking the endpoints. Exactly. So you can think of these maps to MGA if you want. So I define the divisor class here. You can just pull back to B and also maps to here if you want. Okay. Okay. Yeah. Yeah. So implicitly, I always want to mark the special zeros and poles. Okay. These are called Pn, and the intersections I call them as Si to I, S1 to Sn. Okay. But so this has more information, right? It's not directly leaving MGN. It's inside this one. You can think of the Hodge bundle, right? It carries differentials. Right, I have to use that information. There's one more divisor class, which is very important. So think about this way. So what is let's come back to Hodge bundle. Hodge bundle is a vector bundle over MG or MGN. I can pull it back. If you have a vector bundle, then there's or maybe projective bundle, then there's a so-called tautological line bundle class. Say, like the Serres line bundle O1 or O minus 1, right? If you do O minus 1, this line bundle class just means over each point in your vector bundle, the fiber of this O minus 1 canonically stands for the one-dimensional vector spanned by that vector. So that's why it's called tautological. So because B prime transdifferential, let me write down. So there actually is a tautological class on the Hodge bundle, then also on the each strata, then also on B. So there exists a tautological line bundle class. Let me just call it L. You can think of this as really, in a better notation, is O minus 1 on the strata or on B. So that, so look, so B is not only a family of curves, it actually is a family of differentials, right? So each fiber here, so I have a differential, okay? So that maybe I should say this line bundle L restrict to every point. So for a point in B, now I have to write it not only as X marked as Pi, I also have a differential. Let's write it as X and omega and along with P1 up to Pn, where omega is a differential, where omega is 0 minus omega pole is equal to sigma mi pi. That's the total setting, right? Right. This is a family of differentials of type mu given by these mi's, and mark these zeros and poles, whatever. So I have a point in B. So I want to describe this line bundle on B. I have to tell you how to describe this fiber restrict to every point in B. This fiber is canonically generated by this differential class. Right. So that's why it's called tautological line bundle. I mean, this is really the same as defining a tautological line bundle O minus 1 on the like a vector bundle over a variety or on a projective bundle. Okay, if you have a projective bundle, you know what is O minus 1 is. Here I'm just taking this as O minus 1, say of the projectivized Hodge bundle, then pull it back to B, if you want. That's exactly the same definition. Okay, the important thing is that it has a geometric meaning. When I take L restrict to every point in B, I know the fiber of L is exactly spanned by that differential. Okay. All right. Now I'm going to write down maybe the key relation, which is really important, not only for this proof and has several other applications. It's pretty simple, but once you have this relation, you can use it to derive quite a few interesting consequences.
Use the same equation E. Use the same.
Yes, this is B. This is, yeah. I want this as the same. I want to apply this picture in this setting. Because B does parameterize an unpointed curve and with more information. So I still have this picture valid for the proof. I want to keep it. I'm going to actually use this picture, okay? I still have X as my universal curve over B. And moreover, every fiber is smooth because I assume B is a complete curve in the strata of smooth curves with these differentials. There's no nodal fiber, okay? Then I'll show you a contradiction. But let me write down the key relation, which tells us the following. So I have this relative canonical line bundle, omega pi, restrict to each fiber is the canonical line bundle of the fiber, right? And I also have this another line bundle L, but L is not defined on, so omega pi is defined on X, on the, sorry, I should say curly X. But this line bundle L is defined on the base B. I want to compare them, so I have to compare it by pulling back. So L is defined on B, defined on B. I want to pull back the L by pi, and so that I get a bundle over the total surface X, right? Okay, I get two line bundles. Okay. I have another bundle. Let me write it down. So again, so I have n sections, each section corresponding to the ith zero or pole, so just pi, right? And if it's pi, I also know its zero or pole order is given by that integer mi. So I have another bundle. So oxi, let me put this m1 s1 plus s2. I treat each si as a divisor inside the surface, so I get another line bundle class. Okay. These are all like line bundle classes on the total inverse curve on curly X. Okay. So relative dual line bundle, relative canonical line bundle, the pullback of the tautological line bundle to the total family, and then this is another directly defined line bundle on X. You can think of them in this way. Look, let's compare the left one and the right one. Okay. So this one, restrict to every fiber, is a canonical line bundle. So this one, restrict to every fiber, is also the canonical line bundle because this represents a section of the canonical line bundle. The Meromorphic section is okay. That tells us these two line bundles, fiber-wise, are always isomorphic. If you have two line bundles on this family, fiber-wise isomorphic, they only differ by a line bundle pulling back from the base. So I claim they differ by the line bundle exactly this L pulled back from the base. In other words, I have this relation. I take the tensor product of these line bundles, then I recover the relative canonical line bundle. So maybe let me write down what I said. So omega pi restrict to each fiber X is isomorphic to the canonical line bundle of X. And also if this guy restrict to each fiber is also canonical line bundle of X. That tells us they differ by a line bundle pulling back from the base. Some line bundle pi pull back, some line bundle on B tensor the other bundle. This OX sigma MISI. Okay. And I claim this pullback line bundle is nothing but the tautological line bundle. I mean, that actually is not hard to see. I mean, let me provide another way to tell you. I can compare this bundle by, so if I take this bundle, restrict to every point, say I take a point in X, okay? If this point is different from the markings, okay? So then this guy just gives me the canonical line bundle, the cotangent line associated to that point. But this guy is also okay. This guy on the fiber is given by that base differential. I should put omega here as well. If omega is not zero and has no pole at that point, that means I can use omega to span like a true one-dimensional fiber. So that means away from the markings, away from the zeros or poles. So this omega can also span the cotangent line at that point. In other words, these two are really the same away from the section Si. So on each Si, that is on each marked point, say suppose I have a zero of order m, then that means my base differential omega is identical to zero at that point. Then I use it to span one-dimensional fiber. I cannot, right? Because it is zero at that point. That means if I have a zero, then this guy, well, in some sense, smaller than that, there's a co-kernel associated to that point. But that point is not necessarily an ordinary zero. It has a Lagrangian order m. I have to trace it by m times that point. Similarly, if I have a pole, then in some sense, this one maps to here, I have a co-kernel. So I have to correct it by using the minus of that section and with the pole order. In other words, you compare this guy. So they are almost the same away from the sections, and each section you have to correct it by adding the right multiplicity of the zero section or minus the right multiplicity of the pole section. But these are just encoded by these coefficients mi. Okay. So this actually is in some sense a tautological relation, not only for this case. If you have just you can replace by other line bundles, and you have this kind of distinct section of zero poles. You compare them. I think this just follows this sentence from the definition of the tautological line bundle class. So anyway, I sort of explained this in different viewpoints. So clearly, these two differ by the line bundle pulling from the base, and it must be this tautological line bundle. Okay. This is really the key relation. Okay. All right. Once I have that, I can do something. Because I also have this map sigma I from B maps to Si. I have a line boundary relation which holds on X, the total surface is clearly X. Again, I can pull back this relation to the base B via each sigma I, and let's see what we get. So pull this relation back, relation star, via the map sigma I, that is from B to Si, which sits inside clearly X. Let's see what I get. I pull back the left-hand side. I erased, but if you look at your notes, this is nothing but the ith cotangent line class I defined called psi I, right? So let me erase this as psi I. Right? So this is just psi I, the left-hand side, that is psi I. The right-hand side of the star relation of a pullback. Oh, I have the what? I pull back the first term, so sigma I. So that is I have pi composed with sigma I, then I pull back, right? Yeah. Okay. So that gives you sigma I. Right. So. And the other term, I can pull back each. So this is, I can write this as a tensor product of OX M1 S1 tensor OX M1 2 S2, so on and so forth, and pull back, like say, the tensor product of sigma I pull back OX. Say, I already use I, so let me change the index MJ Sj for j from 1 to n, right? So I write this as n tensor product M1 S1, the line bundle tensor up to Mn Sn, and I pull it back by fixing index I. So maybe here I should say fix some I between 1 and n, okay? So let's focus on the I section. I pull back this relation via phi I, okay? So let me simplify the right-hand side. I'm not done yet. This picture somehow blocks my space, so let me move it here. Okay. So the right-hand side, let me continue. I'm not done yet. Continue. Yeah. So this is equal to, look, so if I do sigma I and then compose with pi, so this is identity. So this part is nothing but L. The first term is easy because sigma I composed with pi is identity. So tensor. If I take any other j different from I, look, Sj and the image of sigma I Si, they are disjoint. For any j not equal to I just pull back the trivial bundle because Si and Sj, they are not intersecting. So the only thing I need to care here is when j equal to I. That's the only non-trivial thing I may get. So look, because so Si and intersect Sj is empty for I not equal to j. That tells us if I pull back the O Sj, I get trivial. Okay, so only non-trivial thing left over here is one term, sigma I, pull back O chi M Si. Okay, maybe let me also write it as, I can take this m out, write it at sigma I, pull back O x Si as this line bundle and raise it to the mth power. It's the same thing. It's mi. Okay, that's the only possibly non-trivial line bundle class I need to rewrite. Okay. Well, if you think about this way, I mean, what do we have? We have the, let me also recall the adjunction formula. So now I have this universal, surface, okay? Now B is a curved surface. Now I have this divisor Si sitting inside the surface. So if I apply the adjunction formula to the section Si as a curve inside the surface curly X, what is adjunction? It tells us the canonical class of Si is given by the canonical class of a total space plus the divisor Si, the restrictor Si, right? Okay. And if you think about it, it tells us if I compare the canonical class of the total space, then tensor with the inverse of the canonical bound of Si and identify B with Si, then I just get the relative canonical line bundle restrict to the section Si. Right? Because relative canonical bundle exactly means I take the total canonical bundle modulo the one from the base, but Si is isomorphic to B, whereas Psi. Okay? So this inverse gives me the canonical line bundle. That really means the relative canonical line bundle omega pi is the inverse of OSI with true Si. So that tells us if I pull back everything from where sigma I to B, applying adjunction, so this last term, let me continue writing here. This last term is nothing but omega pi, inverse, that is psi I inverse, restrict to Si and pull back by sigma I. So psi I inverse, tensor Mi, so this is minus, let me write this, tensor Mi. Okay, so this part from the adjunction, okay. So I'll simplify here to there using the adjunction formula. So it's a good exercise if you did not follow all the details. But roughly I explained, so the difference of these two is the relative canonical bundle omega. That means relative canonical bundle omega pi plus Si restricted to Si is 0. That guy tells us that this OSI really is a minus of omega pi restricted to Si, but minus omega pi is minus Psi I. That's why I have Psi I inverse. Okay. Now let's compare the right-hand side and left-hand side. I guess this guy is isomorphic to that guy. Okay? So the two highlighted, like circulated terms tells us I have a relation. Maybe let me write down the, the relation tells us maybe, so maybe let me put it this way. So here I'm using the line bundle notion, but let me also switch to the first chain class notion. So that tells us, what do I have? I get L is isomorphic to psi I raised to mi plus first, right? Okay. So this part is isomorphic to psi I. That means I have psi I raised to the mi plus first. This line bundle is isomorphic to L on B. This for all I. From 1 to n. Okay. In other words, it doesn't matter if you vary I, then you only need to vary this exponent according to the zero or pole order. So this could be positive or negative, whatever, but they all equal to the same line bundle L, the tautological line bundle on the base. So calculation is very short. Actually, this is all the details you need. You're almost done. Now here I really need to, let's recall the condition in the theorem. Right? I said I have a meromorphic differential. That's important. I have mi, some mi is smaller than 0. That means mi plus 1 is non-positive. Okay, so I need to use a set. If these are all positive, the rest of the proof just breaks down, as you will see. All right, so let's see. So that also tells us from here, it really tells us all the psi I tensor mi plus first is really equal to any other psi j tensor to the mj plus first this power for all ij. Okay, I get a relation between this. Okay. Now I don't need this picture anymore. I can erase it. From now on is some just pure some algebraic argument. So let me put two remarks which I'm going to use, and without much explanation. This actually is not too hard. First, let's assume that this is not too bad to assume. Assume the genus is bigger than or equal to 2. This is pretty, harmless, because if genus is 0, I already explained the space is affine is more or less M0n, so it's affine space. There is no complete curve. If genus is 1, you can also treat it by some like ad hoc method. So the harder part is for higher genus. So let's assume genus bigger than 0, bigger than or equal to 2. That tells us the sum of this Mn is equal to 2g minus 2 is strictly positive. Actually, I can even assume, include the case genus equals 1, maybe. That doesn't matter. So that tells us if some Mi is smaller than or equal to 0, then there must exist some other Mj bigger than or equal to 0, because the sum is positive. So my assumption tells me I have some poles. So it forces there must be some zeros. I think it even applies to the case genus equal to 1, but it's okay. But low genus, you can check it by other methods directly. Another fact I'm going to use is that so this psi I class, this cotangent line class associated to each marked point, it has some special positivity property. That I'm not going to prove, but I can tell you a reference later if you are interested. So let's consider this psi I actually is defined on any family of n-pointed curves, right? I can take the family to be mgn if you want, because that's a universal like a family, and then any other family B maps to mgn to pull back psi I. Okay, psi I actually restrict to any. Maybe I put it this way. So if B is a complete one-dimensional family of genus G curves, smooth genus G curves, then the degree of the psi I for each I restrict to B is non-negative. The psi I has positivity property. Moreover, so the degree is equal to 0 if and only if so B is a trivial family, or isotrivial. That means it maps to a point in MGN. Okay. All the fibers are isomorphic. It's not a true family, it's just like some representative trivial family. Okay. So this is some property of the psi classes. I'm not going to prove it here. It goes a bit far and not so relevant to the topic of my lecture series, but I'm going to use it. Okay. It follows basically from some kind of Hodge index theorem applied to this fibration over B. You have to take this omega pi class, a fiber class, and psi I class, and then look at the 3x3 intersection matrix, apply the Hodge index theorem that tells you something like that. And, yeah. And also you need some other positivity divided class, kappa or lambda, you know, on MG. But anyway, let's assume this. Okay, so once I have this remark and fact, I'm almost done, because what I can do is that, look, so I take one Mi which is negative. I take one Mj which is positive. But I know the degree of the psi I is always positive, because my family B is not a trivial family. I assume it's a true complete curve in the family. Okay. So now take some Mi strictly negative and another Mj strictly positive. Okay. I know that by this remark, by this fact, so the degree of the psi I and and the degree of psi j, they are both positive by that fact on B, okay? Okay. But that's almost impossible, right? Because I have a relation, right? If I have mi smaller than 0, that tells us mi plus 1 is non-positive. But mj plus 1 is strictly positive. Okay? Now I just compare this relation. I take the degree. They are equal, they have the same degree. Okay? Then that tells us, from here, it tells us the degree of this guy, because psi I has positive degree, but it raised to a negative non-positive power. So this guy has non-positive degree. And also degree of the other side is positive because this is positive and that is positive. But they are equal because both of them are equal to the degree of L. Right? So that tells us, so these are equal to the degree of L. That tells us my degree of L is not defined, right? It has to be positive, has to be non-positive. Contradiction.
But you need to check the piece, not isotropic.
It's not an isotropic family, right? Because I have a complete curve inside
MGN.
MGN, yes.
But why not in the vertical part?
I guess I have to say B is isotrivial in the sense in MGN, right? Because that means my n markings also cannot vary.
Yes, but the complete curve can be why not inside of the. I mean, fixing curve and then only moving the points or something.
No, that is also called not an isotrivial family, right? Because if I move the point, that means if my ice marking varies, the degree of psi I must be MGN. Yeah. Because if I only have MG, then I don't have the class psi I. Psi I really has the positivity property on MGN. So my B is an n-pointed family. So psi I actually, so it really controls. That means your ice marking cannot vary.
So here isotrivial means the in MGN, not MG.
Yeah. Okay. Then basically that's giving me a contradiction. That's telling me that degree L cannot exist. Right? So that's a contradiction. Because it has to be on one hand non-positive, the other side positive. It's impossible. So you see clearly I had to use the sign difference of n plus 1. I need some of them to be positive, some of them to be non-positive. That's why if all the mi's are positive, in other words, if I'm in the holomorphic differential strata, this method, the last part, so up to here is still okay. The last part does not work. So this trick does not apply. Okay. So
how about the fact?
Which fact?
Is the fact true for the fact, for the fact, do you use the assumption MR is not?
No, this fact has nothing to do with differentials. All I'm saying, if I have maybe n-pointed. No, this fact just tell me my class psi I has positivity result on MGN that has nothing to do with differential. So it's a modular space property. Yeah, this part has nothing to do with the strata H. If you give me a non-trivial n-pointed families of pointed curves, then this psi I has this positive property. So this is a positive property for line bundles on the modular space. Okay, you can find this proof and explanation in the book by Harris and Morrison, Module of Curves. Okay, so that finishes the proof with almost all the details. Okay, any question? Okay, so in the remaining 15 minutes, so let me come back to the motivation of introducing meromorphic differentials, right? Because my result is only about the strata of meromorphic differentials. You may wonder, oh, this looks like maybe not so interesting compared to holomorphic differentials. I sort of explained in one occasion that I represent a meromorphic differential with poles by like an infinite polygon using Euclidean planes with adding a point at infinity. Right? That's what I did yesterday. But I claim using that picture, actually you can get more information for another related topic. I was hoping I can cover it for more material, but now I don't have time. Let me just show you by one example to get a sense why this meromorphic differential naturally shows up when holomorphic differential degenerate. If you understand the following example, then you get a good sense about what in general you should expect. So the last topic or example is called degeneration. Of holomorphic differentials. So let me just do one example. Okay, so let me, actually this example, you sort of seen a shadow yesterday. So let me take a flat surface which looks like the following. I take a big torus with the edges identified in the standard way, okay? Let me call it Y. Okay. Now I remove a smaller torus sitting inside Y. Look at the complement. Let's call it Z. I remove it and look at the complement. Again, so Z is glued in the same way. So remove a small flat torus from a big torus. So let's first check for the remaining part. It still looks like a flat surface with a finite area. And it represents a holomorphic differential. So Y minus Z, and with the edges glued. Actually, this is still octagon. 1, 2, 3, 4, 5, 6, 7, 8 edges. And the 4 pairs of parallel edges glued. And the only thing you have to do is this vertex, you count the cone angle outward. The cone angle is in total 6 pi. It represents a holomorphic differential with a double zero as a vertex. Okay? So this actually lives in the strata. So only one double zero, genes is 2, live in the strata H2. So genes equal to 2. That's another reason this polygon picture can be very bizarre. So this looks like not a polygon, right? I mean, come on. So, but I can cut and represent it in different ways, so it looks like the original octagon picture I showed you. But I just do it this way. Doesn't matter, right? I mean, always cut and paste. Okay, now I want to degenerate this flat surface to go to the boundary of the modular space. So when I compactify, so say H2, I need to know how this kind of thing degenerate. You can cook up any kind of degenerate, make some edges short and shrink something. Let me do one example. Let's shrink Z first. So I can make the removed torus arbitrarily small. But as long as it's still like a small torus, it remains in the strata H2. Unless it goes to a point, then certainly it disappeared, right? Let's just take the limit. Just by the naive limit, if I shrink Z to a point, then what you get is that you still keep the outside torus Y, and you get the limit point. Let's call it Q. Okay? That represents the limit of the shrinked torus Z. And this is still a flat surface, right? But it is in which strata? It belongs to the genes 1 strata, right? There's no zero, just H1, right? Genes 1 is just a flat torus with one special markings, right? In some sense, it's M11, and with a non-trivial differential. And you may wonder, okay, that's it, I got a limit. But that's not it, because this is genes 2. How can I get just the genes 1? I'm missing something, right? If you think of from the Dirichlet quantification, I need to keep the arithmetic genus to be 2. But I'm losing genes 1. So my genes 2 surface suddenly becomes genes 1. It's weird, it's not a flat family. Right? If you do topology, it might be fun, I mean, but for F geometers, it's not good. So let's recover the other missing components. That means there's something that is hidden under the like infinite, like the arbitrarily small metric on Z. Well, let's recover it. I claim you can think of this picture from another viewpoint. When I say I shrink Z, if you stand inside Z, so this is the same as saying I expand Y arbitrarily large. Because in order to understand the Riemann surface behind the differential, I can rescale my differential, right? When I say I shrink Z, I can always rescale the whole picture. Does not change the underlying curve, only change the differential by size, right? I'm saying, okay, I can think of Z still fixed and let Y arbitrarily large. So it's almost the same thing, right? I can also alternately consider expand Y. If you do expand Y to arbitrarily large, that is the picture I showed you yesterday. By removing this parallelogram from the Euclidean plane, then you gain a double pole at infinity. So you add a double pole, let's call it P. At a point at infinity. Well, I mean, I explained this actually leaving the strata genus 1, but it has a double zero still as the vertex of Z and a double pole at P. So this is strata 2 minus 2. I have a double zero here and a double pole at P. Okay. Now we are good because this is also genus 1. That is genus 1. If you combine these two pictures, you actually recover the total genus 2. Okay, so that means we sort of get the missing component, and nevertheless, on the missing component, there's some information. You actually see this missing component using a Meromorphic differential with some suitable order of pole. And let me rewrite this picture in our context using like algebraic fabulations, and you will get a better understanding of what's going on. So in any case, I just have a genus 2 curves with a double zero, right? Degenerate to some other curve. So let me describe the central fiber. I have to glue these two genus 1 curves, Y and the bottom one together, and mark some like special points and mark some node somewhere. So the picture looks like, so here I have this guy, let's call it maybe, I don't know, xt. And here let's call it x. When t goes to 0, that means I shrink Z to 0 or expand Y to infinity. The picture looks like, so here's my t line. So when t goes to the central point, so I have a nearby, this is xt, with a double zero here, the double zero. And when it goes to the limit, clearly the double zero goes to this Meromorphic component, right? It's here, so it's the interior point. And this P you should think of somehow, although this component looks large, but still, because that's my Y becomes arbitrarily large, this one still sits inside a very small neighborhood. In other words, you should glue this pole P to that limit point Q as a node by gluing these two curves together. You have something like this. Now this is one flat torus in this strata, still denoted by Y. This is another thing, let's still call it by Z, by abusing notation. So then this Z component with the Meromorphic differential contains the double zero. The double zero goes like here. It's still double zeros, but here I identify P equal to Q to glue to a node. So this gives me a double pole for the Z component. Okay. That's a double pole on Z. Okay. So both of Y and Z are genus 1. So it's genus 1, that is genus 1, here X is genus 2. So it's a flat family of genus 2 curves with one marking. This double zero goes to the Meromorphic component. On Y, I do get a holomorphic differential, nowhere vanishing. But this node becomes a pole for the bottom component Z. And it has more information because I cannot take two arbitrary points P and Q because they have to be two torsions to each other on this Z component, right? That means this double pole and that double zero, there are two torsions on the genus 1 curve Z. So in general, so the idea is that if you have a derivation of holomorphic differentials, no matter how complex the picture is, in the end, your central fiber will be some stable pointed nodal curve. And you will necessarily have some Meromorphic differentials on some reducible component. And then at each node, you have some compatibility condition. So this node is an ordinary point on Y, it is a double pole on Z. If that node is a 0 on Y, it has retrieval pole on Z. There is some relation between the 0 order and pole order at each node when two components meet. And there is some other conditions that impose to such a degeneration. I'm not going to talk about it here, but as one final remark, so if you consider from the viewpoint of degeneration of canonical lamp bundle with sections. So again, so let's call this total family curly X. So I have the canonical lamp bundle of the nearby fiber kxt as t goes to 0. What is this limit? Well, you can see that, okay, I have a nodal curve. I can just take the canonical lamp bundle or dualizing lamp bundle of the nodal curve. But this limit is not quite unique. I can really take the total surface and twist it by the component of y and z, and my restricts to the central fiber, I get different limits. So this picture actually tells us if you only take the canonical lamp bundle without twist on the central fiber, I mean, it will have degree 1 on this genus 1 component, but I require it to have a double 0. That makes the section coming from this double 0 completely vanish on this component. From this picture, completely vanish, that means the surface shrink to a point. But I want to see the surface. I don't want it to shrink to a point. I've twisted by the z component to recover it. But when I twist to make it become degree 2 here, then that introduces a pole at that node. That's why I will see a double pole. So this idea comes from the Eisenbach-Harris limited linear series. So that's the algebraic interpretation of the degeneration here. So these two pictures are the two aspects of degeneration. They correspond to different limits of the canonical lamp bundles. One could be some like the canonical lamp bundle of the central fiber, so x naught, or I can do some like a kx naught tensor with any other lamp bundle supported on the central fiber, right? Because it does not change the nearby lamp bundle. I have to do something like this. See why. So if I do this one, it will have degree 2 on the z component. That can afford a double 0. But then the price you pay will introduce a double pole at that node. All right, I think I'll just stop here.